Welcome everybody. This is the next section in Chapter 3. So Chapter 3, Section 3, Basic Vector Arithmetic. I'm going to spend a little less time on this section than the book does, just because I don't think it's super critical moving forward. Some of the concepts are very important, which I'm going to stress those, but some of the actual example problems and work, we're not really going to use the techniques in this section later on. So it's just not really worth spending too much time on. So let's go through and see what is critical from this section, and we'll talk about that. So we've all had a little bit of experience with vectors so far, but we haven't really gotten into some of the nuts and bolts, some of the arithmetic and things like that with them. So first thing to understand is vectors are equal if they have the same magnitude and direction. So that seems pretty obvious, but what you'll see from the diagram there in figure 3.5 from the book is they may not look exactly the same. Like, they don't necessarily have to be right on top of each other in the exact same location. By same magnitude and direction, that would mean they do have the same length, because that would be their magnitude. The magnitude of the vector graphically is its length. The same direction just means that it has to essentially be parallel to the other vector. So they don't have to be right on top of each other. As you can see here, all these, there's four vectors there drawn, all over the plane, and none of them are overlapping each other. None of them have the same starting point. However, they all have the same length or magnitude, and they're all pointed at the same. They all have the same theta or angle or radian measure. They're just not on top of each other. So that's graphically, that's how you could tell if two vectors have the same slope, same angle, however you want to look at it, and also the same length magnitude. That's how you would say two vectors are equal. So what we're going to get into now is doing some vector addition. The way you add two vectors together graphically, or how you visualize it, is they say tip to tail. So in this case, in the graphic figure 3.8 there, we have a plus b. And then, so you take the first vector a, draw it anywhere, draw it in space. So what we have here, I'll walk through it a little bit step by step here. Let me grab my pen. So if we have vector a and we want to add vector a, so we draw vector a first. Oh, I did that backwards. So we draw vector a first, like this, and then it's called tip to tail. So you have the tip of vector a, and then you start by drawing the tail of vector b in that location. I really got the instant things on. There we go. And then you put the tail of vector b to wherever vector b is going. In this case, it looks like right there. I'm just making up angles right now. Jeez, the shape thing is really on now. It's just auto-correcting my text to shapes when it can. So anyway, so that's vector b. And then what we have is, when you add those two together, this is called the resultant vector r. Jeez, dude. So this is the resultant vector, or the sum of a plus b. So where r is equal to vector a plus vector b. So if you add two vectors together, you get a third vector, right? A resultant, or the sum of two vectors. And you can add multiple vectors. You can add 3 vectors, 4 vectors, 5. You can add an infinite number of vectors. Vector addition is very similar to algebraic addition, or just, I guess, arithmetic addition, in that it's commutative. So a plus b, or b plus a, as you can see in the diagram, like once again, figure 3.8, if you're starting at the point, right, where's my cursor? Where's my mouse? Or my pen? There we go. If we're starting at this point here, this is going a plus b, and this is going b plus a, but you see you end up at the exact same point. So regardless of whether you do a plus b or b plus a, as you can they have diagrammed here, the vector r, the resultant vector, is equal to b plus a, vector b plus vector a, or it's also equal to vector a plus vector b. So the order you add them does not matter. In most cases, there's not really going to be a better way to do it. You just pick one and go with it. Like I said, and kind of where I'm going with this too is, it's important to be able to represent vectors graphically, but not in most cases we won't be actually doing the mathematics like this. We'll draw these to get a nice picture of it, to understand kind of what's happening, but we're not going to do our algebra and our math calculations graphically like this. Like, we're not going to calculate vector r from from the picture necessarily. We're going to have a few other techniques that come up in section 4 that we're going to use way more. The next figure here, figure 3.9, is just more an illustration of the commutative property of addition and vector addition. If you have A plus B plus C, it doesn't matter if you do B plus C, then combine it with A, or if you do A plus B, then combine it with C, then add it to C. You always end up in the same spot. You can see that from the pictures up here. So we have, this up here is A plus the quantity of B plus C, and this is the quantity A plus B plus C. So in both cases, you end up with, you can see it's the same vector, just the way you end up going there is different. This could be a case where you may want to do, like if you were adding 3 or 4 vectors, there may be some convenience in combining or adding some of them first and then a third. Or if you have 4 vectors, you could even add 2 of them together, then add the other 2 of them together, then add the sums of those together. Depending on the characteristics of each one, there could be ways where, yeah, it might be a little bit easier to pick a certain path. But as long as you follow all the mathematical rules, you'll always end up in the same spot. So you don't really have to sweat it too much. So subtracting vectors, once again, just like arithmetic, is the same as adding a negative of that vector, right? So vector A minus vector B, another way to say that or to visualize that is vector A plus negative vector B. And that's just like addition, or excuse me, that's just like subtraction with numbers, right? You know, saying 7 minus 4 is the same as saying 7 plus negative 4. So adding a negative number is the same as subtracting a number. One of the big things to keep in mind here is that A minus B is different than B minus A. Once again, just like numbers. 7 minus 4 is different than 4 minus 7. So that's the thing to keep in mind here. So just to list, like I said, so A minus B, these are not the same as vector B minus vector A, right? This would be vector B, plus negative vector A. So now, I guess the question that arises is what's a negative vector, right? How do you come up with the negative? So the negative vector is same magnitude in the opposite direction. Oh yeah, so I have that portion highlighted there. The vector A and vector negative A have the same magnitude but point in opposite directions. So you can see this would be an example of A and negative A here. Another way just to, like I said, just another illustration of that. So you have just some vector here in space. We'll call it vector A. I'm just going to literally, I'm going to copy this. So here's my vector, and then I'm just going to rotate it. I can't do it. Okay, 90. I couldn't do it 180, but just rotated it 90 degrees twice. So these vectors still have the same magnitude. They have the same length. They're just in complete opposite directions. So this would be an example of negative A. So the graphic here in between my two illustrations, the dashed line in this case is vector B, right? So this is, if you were adding A plus B, your resultant vector would be this here. This would be your resultant vector. But since we're doing A minus B, you take the negative B vector, which is, like I said, the dashed vector is B. This is negative B. So, and then once again, you still combine them the exact same way. You still just do tip to tail. And then your resultant vector is from the tip of the first, well, I guess that's, the tail of your first vector to the tip of your final vector. So that part is still the same. Coming up with that resultant is still the same as addition. It's just, like I said, because it is technically addition. It's adding a negative. So A plus negative B, you end up down here. If you just had A plus B, you'd be up here. So yeah, that's essentially how you add or subtract, multiple vectors. And, same thing, you could have A minus B plus C plus D minus E minus F. And it's just all the same. You still keep drawing those vectors, tip to tail, tip to tail, tip to tail, and just keep going until you get to the end of that chain, and then your resultant is that final from the tail, excuse me, I keep saying tip and tail backwards. The tail of that first vector all the way to the tip of that final vector. Another concept in this book, or excuse me, in this section, is scalar multiplication of a vector. So if you have a scalar quantity, in this case, that's what m is here. So if you multiply a scalar by a vector, you multiply the magnitude of that vector. So if we had, excuse me. So if we had vector A, so that's vector A, and then we wanted to show 2A, it would literally be this line doubled in length. Let's see how accurate I can get with doubling. That's pretty close. But this would be 2 times the size of this. Just the lengths of the vectors. They would be in the same direction. That's pretty close, same direction, I think. But double the magnitude, same direction. So that's it. Scalar times a vector, that's how it works. So keep in mind, we have not done multiplying 2 vectors together. That's a whole other can of worms. We're going to get into that later. But it does not come up now, and it's not really relevant for what we're going to be doing in terms of our kinematics and our equilibrium, our forces at equilibrium. Like I said, we'll get into it later on with we'll need it for torque and a lot of circular stuff, but we don't need it right now. So all we really have to worry about is adding, subtracting vectors, and then the scalar thing comes into play with our kinematics, which we'll deal with. But my two little text notes here is this is kind of what I was talking about in the beginning. The graphical method, it's good. It's very important to be able to visualize how these vectors are combined by adding and or subtracting or scalar multiplication. Like the concept is very important. You do have to understand what's happening. On the flip side, graphically, you won't have to do calculations based on this graphical method really after this section. I know this section has some example problems. I highlighted that down at the bottom. If you want to take a look at how it kind of works, example 3.2, a vacation trip. I think it's example 3.2. That walks you through how you would solve for a resultant vector using graphical vector addition. It uses the laws of sines and cosines. It's not super complex, but there's easier methods, and it's not super related to kind of most of the things we're going to be getting into. Most of the things we get into with two-dimensional kinematics and even our forces, we're mostly going to be dealing with the XY plane. So what we cover in the next section is going to be much more relevant to what we're doing moving forward. So I don't want to downplay this section too much, like, oh, just skip it, don't worry about it. But at the same time, I don't want you to spend a lot of time trying to graphically solve problems. Big thing here is I just want you to conceptually understand what it looks like, how to draw vectors, and how to properly draw the sum of vectors and subtraction of vectors. So that's really what I want to get out of this section. And then moving on to 3.4, we'll talk about doing some more of the heavy lifting with vector adding and subtracting vectors more analytically or algebraically.